So now that we've talked about the three different types of hazards, let's talk about the performance impact they have. So the performance is about keeping the pipeline full in a pipeline processor. And we've seen how the hazards can introduce empty slots in the pipeline. We can have bubbles or no-ops when we're waiting for results. The load, store, and branch delay slots can force us to have bubbles if we can't find instructions to put in them. And we can have bubbles while we're waiting for resources. So if we only have one instruction memory and we have to wait for that to use it. These bubbles reduce the throughput of the pipeline because they're not doing useful work. These are wasted cycles when we put them in there, and that's why we drew them as little bubbles instead of useful work. So if we want to get this speed up of n for an n-stage pipeline, we need to keep as much work as we can in the pipeline. That is, we need to have as few bubbles as possible. And what you've seen is we've gone to extremes to avoid these bubbles. We've added lots of logic and complications to the processor. We changed the register file, we moved the branch calculations around, we added forwarding paths and forwarding logic, and we had the compiler understand the details of the pipeline. So the compiler needs to be able to put instructions in the load, store, and branch delay slots. So we've gone through lots of work to try and get rid of these bubbles. Now let's take a look at how significant these issues are. So the data I'm going to talk about here comes from figure 3.26 in the book, and these are from particular benchmarks that are typically run to see how fast processors are. So let's take a look at the impact of the load, store, delay slot. So if we go through a bunch of applications and we look at what percentage of the instructions are load and stores, we can see the results here. So load word is 18.6, store word is 7.6, and there are a few other load and store instructions. So in total, 34% of our instructions are loads and stores. Now we have a 1-cycle delay on loads and stores. So what's the performance impact? Well, 34% of the time we're going to spend 2 cycles, and the rest of the time we're going to spend 1 cycle. So this means we're going to have an average of 1.34 cycles per instruction. So this is a 34% slowdown versus the perfect pipeline. So in the perfect pipeline, where we keep all of our slots full, we have 1 cycle per instruction. Here it takes us 1.34 cycles per instruction because of this load, store, delay. Now of course this assumes we can't fill them with useful work. If we can fill some of these with useful work, then they're going to be less of a performance problem. Let's take a look at the branch delay slot. So again, we can look at the frequency of branches. So we see that 17% of the instructions are branches. You can do the same calculation where we have a 1-cycle delay on branches. So 17% of the time we're going to take 2 cycles, and the rest of the time we're going to take 1 cycle. So this is a cycles per instruction of 1.17. That is, on average, we're going to spend 1.17 cycles for every instruction due to these delay slots. So that's a 17% slowdown due to branch delay slots. And again, this is true if we can't fill them with useful work. Now let's take a look at the memory accesses. So we have a total of 34% of load stores. If we don't have separate instruction and data memories, then we need another cycle of delay. So that'll be 34% additional slowdown. And if we don't have separate instruction and data memories, we can't really avoid this. So we're going to have this every time we access memory. So as you can see here, this is really significant. We're talking about 34, 17, or 34% slowdowns due to these delay slots. So when I emphasized earlier that pipelines are only effective if you can keep the pipeline full, here you can see some of the difficulties in actually keeping it full. So a question, why are these delay slots causing slowdowns? Well, the answer is the pipeline isn't full of useful instructions. The performance loss we have is because we can't find useful work to do all the time. This means we have no-ops in the pipeline, and those no-ops waste cycles, so we don't get the full speed up. So let's talk about some idiosyncrasies of pipelines. So we've seen how MIPS exposes the load, store, and branch delay slots. This means the compiler has to take it into account, and the architecture does not deal with it. Now this is a design decision. The people who designed MIPS decided explicitly that the processor was not going to take care of this. And why did they do that? Well, when MIPS was designed, logic gates were expensive. They didn't have that many transistors to work with, so they felt this was easier to solve in software than it was to solve in hardware. Another part of this is the MIPS design philosophy. MIPS stands for microprocessor without interlocked pipeline stages. That is, MIPS is explicitly a design that does not detect hazards and stall. This is left up to the software to do it. So a legitimate question is, was this a good decision? And the answer is no, this was not a good decision. These days we know we have more transistors than we know what to do with them, and it would be much better to have the hardware take care of this than have to change the code for every new version. So let's think about what this decision means. So if the compiler has to take care of the processor, it means the compiler has to know which version of MIPS you're targeting and how many delay slots it has, or your code will crash. So if you get a new MIPS processor that has an 8-stage pipeline or a 12-stage pipeline, you're going to have to recompile your code, and the compiler is going to have to know which processor you're using. So this is clearly totally impractical. Nobody's going to recompile all of their code just because they get a new processor. So what happens instead? Well, instead, the newer versions of MIPS have to pretend they have the same pipeline. So even though there are newer versions of MIPS with 8 and 12-stage pipelines, they still have to pretend that they have a 5-stage pipeline and make sure they take into account the load and store and branch delay slots as if they had a 5-stage pipeline when they no longer do. So this now makes the processor harder because they tried to save a few instructions earlier on in the design. So this was clearly not a good decision. Let's take a look at some of the implications of this. So here's a slide from 2012 presented by Oracle, who bought up Sun, and they're talking about changes to the SPARC microarchitecture. The SPARC microarchitecture came out about the same time as MIPS, so this is about the same level of design. So one thing they're talking about how they accelerated constants, 64-bit constants, down to 2 clock cycles. Okay, so remember when we were writing MIPS instructions, how hard it was to get a 32-bit constant? Well, even today, people are changing processors to make it faster to load constants. Okay, that's a nice change. What else are they doing? Well, look at this title here, no-op squashing, code size reduction. They're trying to get rid of no-ops because they still have a delay slot. So this is now 20 years later, and they're still trying to deal with the problems caused by delay slots that were originally in SPARC when it first came out. So 20 years later, people are working very hard on modern processors to handle the mistakes that people made designing them 20 years ago. And the reason they have to handle these mistakes is they can't get everyone to recompile their code. If you could just have everyone recompile their code, they could just change the architecture. But once you have people using an architecture, you're stuck with it. And so you have to make changes in hardware. It's very hard to change all of the software. So let's summarize what we've talked about hazards so far. So hazards exist when we have multiple instructions that want to use the same resource or the same result. They occur because we're breaking the ISA's promise of serial and atomic execution. So remember, the ISA promised that instructions execute one after another, and each instruction executes entirely before the next one. And programmers write their programs this way. You write branch and then add, and you assume that the branch will be finished before the add after it. But the pipeline doesn't do that, and so the pipeline breaks these promises, and that's why we get hazards. We can fix many of the hazards by adding logic to the processor, which helps us move results around. So this is forwarding or having extra hardware to calculate in other places. Some hazards can't be fixed, and we can't fix these because we need a result that's in the future. And so this is why we have memory access delay slots and branch delay slots, because we can't get the results because they're not calculated yet. MIPS made the decision to expose these delay slots, but this turned out to be a mistake. When they first did it, it allowed them to get a little bit of performance and be a little bit simpler, but now every processor that uses MIPS has to take these into account, even though it has a different pipeline these days.